Mario as well, but Marcus is a research associate and PhD candidate. I don't know if that changed, Marcus.
Yeah, I'm still also that.
All right, so his interests include compact modeling, TCAT simulation, and characterization of transistors, in particular HBTs. He's been involved in several software projects as part of, and he's part of a startup called SemiMod. So I invited Marcus based on SemiMod's announcement of their beta phase of their Verilog A compiler called OpenVAF. So based on Marcus' email, right? Please correct me, Marcus. There are three main use cases here. The first one is integration of open source PDKs into open source simulators that employs models that cannot be simulated currently. The second case is use of open source simulators as backend for model parameter extraction and model development. And the third case is Verilog A standardization and development. So I'll let you give us your update and
Yes,
please.
thank you so much, Mehdi. The information was correct, but the focus today is not the Verilog A compiler. We will also show it, but the goal here is really to show the whole modeling infrastructure that we have at SemiMod. So yeah, I will first motivate to talk, and then we will have an overview of the parameter extraction system we are using with open source tools almost only. Then I was inspired by the guys from ETH Zurich with their SEKV model. I thought it's really cool, so I chose it as an example.
EPFL in Lausanne.
Sorry, EPFL, exactly. And then, well, when we talk about SEKV, we kind of have many things not there that you will have with a real model that you could have in a PDK. So I will mention them and then we can have a discussion. So we all know now that the Skywater models have some issues, and there has been continued interest and talk about how we can improve the situation. So far, there have been some activities in that direction, but from the modeling point of view, not so much. There's a shared document by Tim Ansel from Google, where he talks about automated parameter extraction using open source tools with the goal to improve PDK quality and push the open source community forward. So Vladek, Tim Ansel, me, and Sadayuki had some discussions in the last months. So far, we don't have a clear direction, so I hope that I can help steer the discussion into a clear direction today. So the goal is that I would like to show the existing open source modeling software with SAKV as an example model from our SemiMod perspective. Of course, other people might use different tools. Then I would like to explain briefly the software development steps we need to undertake in order to enable EKV or BSIM parameter extraction. And I also want to give everybody an idea how parameter extraction looks in practice, because not everybody in this group has extracted a model so far, I think. And then we can have a discussion. So what do we need for a parameter extraction system? So this is a long list. So we want to be quite modular because there's many different models. There's different sources of measurements and there's different circuit simulators. And usually we need the equations and also some way to simulate a given model. So we need Verilog A interfaces, both for model parameters, equations, and circuit simulators. So one topic that is also important, I think everybody, all the modeling engineers basically will agree that we need a graphical user interface, because during modeling, we select ranges of characteristics and then tune or optimize parameters.
Sorry, interrupting. Can all others who are not talking, just following presentations, mute the mics, because there is a lot of noise coming. Sorry,
Thanks, Vladek.
Please continue. Eric, okay.
So the circuit simulators that we usually interface to are ngSpice, XSize, Spectra, and ADS. And we need to have a DC, AC, noise analysis, and maybe transient simulation mode. When we talk about real-world modeling, we don't have one transistor at one temperature. We have lots of transistors at different temperatures, geometry, statistical stuff. So we would have usually a lot of data that we need to handle in some way. And the parameter extraction steps are usually model or at least device type specific. Somebody really has some noise going on here.
It's
Lalek,
Eric.
do you know who it is?
Can host mute all others except the speaker? Mehdi, can you mute others except the?
I think it's only Rob who can do that.
Or Rob?
Yeah, I'm muting myself to respond. So let me see what the source of the issue is.
I think Eric has other call.
Yeah.
Okay, perfect.
Okay.
Thank you.
Much better. Thank you.
So yeah, and the last point is we need to have a way to document our stuff, not manually, so automated. So if we draw this is from a paper of us a long time ago. We have this overview of the system, and I put some red terms there that denote the tools we are using. So our parameter extraction system is called DMT, and we have open sourced a large part of it. And that's basically the glue where everything comes together. For data management, we use Pandas, which is a very popular library, especially for machine learning and stuff in Python. For circuit simulation, we use many different simulators, but of course, if we talk about open source, and GSpice and XSize are the main tools. For accessing the models, we use a tool we have developed called Verilog AE. That gives you an interface to the contents of a Verilog A file inside Python. So you can evaluate the model equations, and you can have all information regarding model parameters and interdependencies between model equations. Since a few months internally and since a few weeks, we have released our Verilog A compiler OpenVev that's already integrated into the pre-master of ngSpice. So that's what we use to simulate models with ngSpice, because it does not implement many models. I mean, it's a lot of work to manually implement models. So we have 3 tools I want to show today: OpenVev, Verilog AE, and DMT. And of course, we will also see ngSpice with the OpenVev integration. So before we start with the hands-on demo, I will just give a quick overview of the model we will be using. I think it's a really cool model. I'm repeating myself. So SEKV is a really good vehicle for parameter extraction because it's so simple and small that everybody can understand it. And there's both analytical and numerical parameter extraction steps involved. So a lot of the parameters, I mean, it's only 4 in this case, have extraction steps where you do not numerically optimize some circuit simulator or something. You can basically, by analyzing the model equations, get them straightforward. I will show you how exactly in a minute. So we have these 3 equations, and they basically only specify the drain current as a function of gate source voltage. This is a simplified overview. So we have basically only one implicit equation for the drain current, and that's what we will be using now as an example. So we need to determine the parameters of this drain current. So if somebody could please confirm that you can see my Visual Studio Code right now.
Yes, I see your screen.
It's your Visual
Thank you,
Studio.
that's perfect. I prepared 2 scripts that I want to walk you through. As I said in the beginning, this is just how I do it, and this can inspire you, or we can also look forward how we can proceed with Semimod, or somebody else does it. But these are the open source tools we are using, and we will just now demonstrate them live. So the first tool I would like to show is Verilog AE. So Verilog AE is a front end to our Verilog A compiler that you can basically install with pip. So you would just need to write pip install Verilog AE in your terminal, and then it would be installed. So it's pretty simple to install. And then we can load Verilog A files. So this is just basically a path to the Verilog A model I wrote for SEKV. So we can load the model, and then we have also a model card. And now we can do many things. So the model object has, of course, parameters. Oh, not parameters. What's the name? Paras? Yeah, I think paras. No? Perfect. Wait. Yes, so it was model card. So we have only 4 parameters in this case: n, iSpec, VT0, and lambda c. And we get all the information about these parameters here, like the description and the minimum and maximum value. But this is not, of course, difficult to parse. But what's more cool is we can mark equations in the Verilog A source file and evaluate them in Python. So let's look at the SEKV model. So we have here the drain current variable, which is just called I, and I wrote retrieve in front of it. Now, what we can do is we can really calculate this variable from Python because it's marked with the retrieve attribute. So if we look at the model card, the model SEKV object, we have functions. In this case, only one, no, 2 actually, I and GM I retrieve, and we can evaluate it from within Python. So if we execute this, we have to give it the temperature and all branch voltages. And then we can evaluate the drain current in a millisecond. Of course, this is not a circuit simulator, but at, for example, low currents, the series resistances are not important. And in this case, the model is so simple that there's not even a series resistance. So this is exact. And we can use this function directly for optimization and other stuff. Of course, the function of the drain current function of this model is super simple, and you can easily implement it yourself in Python. But if you have big models like real EKV or others, this saves you a lot of time. And what we can also do is, using the parameters attribute of the functions, we see all parameters that influence the value of a function. Of course, here we have only one function in the whole model, so all parameters influence it. But if you're new to a model and you're dealing with different models, this is super nice to find which parameters you have to look at for a given equivalent circuit element. So I said earlier, SEKV is simple. How does it look for a real model that you could use in a PDK? So we can do the exact same with model EKV, and now we have loaded the full EKV model. And of course, the full EKV model has way more parameters. So these are all the parameters you would need to look at if you want to extract the model, and you need to know what they mean and how to extract them. And of course, we can also evaluate the much more complicated drain current function of this model now, without having written a single line of code actually apart from the function call. Did I not? Oh yeah, I did not execute that line yet. No. So now it works. And now in this case, if we proceed until here, the parameters that influence the function are much more interesting because we have a much bigger model. So these would be the model parameters to look at when optimizing just the drain current. Of course, not all of them need to be optimized, but these are just all that can influence the variable. Okay. So finally, we can plot all of this. So for this, I need to execute a script in terminal. And this would be the drain current of SEKV and EKV with default model parameters, without having written any lines of code, apart from the model calls and the plot call. So how can we use all of this for parameter extraction? Here I have prepared a small script where we extract the parameters of the model. I have 2 switches here, automated extraction, because people have been talking about automating all of this. So let's put it to false first. And let's use the SEKV model first. So I have here some switches. If SEKV, we will load the corresponding model card. So first we define the model. Again, we use the Verilog A defined model. Then we load here the measurements that have been done by Akin Aktürk from Cool. I forgot the name. Something with Cool.
CoolCAD.
CoolCAD, right? And so he has measured lots of devices. So we have some method here to select some reference device to extract. We have defined the technology. This would usually define equations for scaling the models. And we have also some specifiers. While we import the data, because all the measurement engineers have different naming schemes, we define a grammar that is unique inside our extraction environment. And this specifier here defines this grammar. We define an extraction object, and then the core part are the steps. So each step has the same structure. A step is a class that inherits from a generic class. It has a name. We give it a model card, a library with measurements, and this thing here is what we call at Semimod the filter. So here we would select all data at 300 Kelvin with drain source voltage 5 volt, gate source from 0.3 to none, and base bulk 0 volt. We give it the Verilog A model, and he will also use only measurement data that has this in its name. We define some parameters to optimize and some other specific parameters that are specific to each step. So we can build the extraction flow by chaining these steps. And in the end, we can call a GUI. So I will just start this now, and we will see our extraction GUI. So this is the GUI. This is a really basic GUI that we have written 3 years ago. It's functional, it's working, but it could be way better, of course. So all the steps we have seen here in the script are now to the left, chained together basically. Each step has a main plot where you can use this tool here to select data. You can optimize equations that are defined in the Python code. And you can have additional plots, but in this case, the step has none. And each step has its own local model card. And there's also a global model card. So very similar to Git, we interact with the local model card and push only the parameters here, you can select it, to the global model card that we have optimized. So as I said, SEKV is a really nice model because, for example, when we plot ID over GMVT, we can just take this value at very low current densities as n. So we have optimized this now. We like the value, so we select push, and then we press here push. Now the value we have optimized is in the global model card here. So the next step, we optimize only in the high current region. There, if you plot ID over GMVT against ID, according to the paper of the model authors, you get iSpec. So we have implemented this, and now we have done it. Always we have measurement data symbols and lines model. So we have now a good value for iSpec, push. Next we optimize on GM. So now in the GM extraction, we have actually called the full model equation using Verilog AE, and it's pretty fast because we don't do a full circuit analysis. Now we have the last step where we take the Verilog AE equation and optimize on the raw data. So depending on what you select here, of course, you will get different results. And you can also use different normalizers and stuff and other things. And what you can also do, what I forget to say, is you can also hand tune parameters here and directly see the impact. And you can select the parameters you want to actually optimize. So for example, I like the value of n, so I will deselect it. I will optimize, and now we have a pretty good fit here. So usually what we do in the end is look at the circuit simulation. In this model, because the model here is so simple, there's no much difference. So if you go to the circuit simulation object, which is called xverify in our infrastructure, we pull the parameters and we see we have a pretty good model, at least if we look into the linear scale. If you look into the log scale, I think it's not that good yet, so we could optimize more here. But I won't do that today because that's not the focus here. So just you have an idea now how the extraction looks with our tools. You could optimize this more and more. So what we can also do is, if we select all the ranges in the data that we want to optimize on, and we put them into the script like this, we can do something that comes close to automated extraction. So we would activate automated extraction, and then all of the steps take their default ranges for the data and call their optimizer. And then they push the optimized parameters and pull off the previous step. So this is as far as we have come to automated extraction. So now all the steps have optimized themselves using this data, which we have put into the script manually once. So I looked at the data as a modeling engineer, I selected the right and put it into the script. And now we can do circuit simulation again, and it looks perfect. I mean, not perfect, but not bad, let's say. It's a very simple model too. So what do we do if we want to change model? So the whole infrastructure we use is extremely modular. So what we just do is we say false as EKV. We load the corresponding model card of EKV. We load the appropriate model, which is linked to in the model card. Everything else stays the same. And yeah, actually, all the remains of the script stay the same. Just these steps, which are model specific, like the extraction of N at low current densities, we will not do now with the full EKV model. So I'm no expert for EKV. I have never extracted a full EKV model, but just we change the model now. And let's deactivate automated extraction. So now we just load the other model. Nothing else changes. And it doesn't look that good anymore, but we can, oh, I didn't optimize yet. So let's optimize. So here I basically just selected some parameters that I looked at the model for 10 minutes and I thought these would be the key parameters. So now we have a pretty good fit, huh? So I didn't spend a lot of time on this, actually less than half an hour. But of course, you see now the parameters we have extracted are of bad quality. For example, this is, I think, this is some physical parameter. I forgot the
Threshold
name.
voltage.
No, this is something else in the model.
GTO is threshold voltage.
Okay, so whatever. So I selected these parameters, and I don't know exactly what they mean even. I'm not an EKV model expert.
Threshold voltage is threshold voltage. So
Yeah, sure. But I mean, what I want to say is these are not necessarily good parameters we have now. I just did a very stupid numerical optimization. And it kind of works for this one characteristic. But if we would now go through the full measurement data, we must make sure that the model parameters actually make sense. We will see the issues if they don't make sense later. So actually, this is all I wanted to show with respect to our graphical user interface and the extraction flow. So for in Semimod, we only extract at the moment HBT models. This is our specialty, and we do software engineering. But we could easily also put here, by defining the appropriate steps for a MOSFET, we could build the same thing for a MOSFET. For example, the EKV model. Let's go to the slides. Back. So, sorry, before we continue the discussion, so what did we not consider? So, as I said, and showing with the EKV model, a realistic model has many more equations and parameters and many more parameter extraction steps. So for example, for the HiCam extraction we do for our customers, it's at least 30 extraction steps. Then we have model geometry and temperature scaling. We want to model them almost over the whole range where you can bias the transistor without destroying it. So inside the safe operating area SOA, we must make sure that the extracted model parameters somehow fit into the PDK. We have also modeling over frequency and transient effects like trapping and stuff. statistical modeling, and in the end, in practice of modeling, at least from our perspective, some parameter tuning is necessary. So we extract many parameters using analytical steps. We have sheet resistances, contact resistances that allow us to calculate equivalent circuit elements, but some tuning is always necessary in the end. And this is extremely difficult to automate. And what we also need to have is some kind of automated documentation. But this is all stuff we can in principle do already with DMT. So I think the test chip that has been designed by Mehdi and his group is a really excellent improvement compared to the previous test chip. So this can help us to move forward. At least I know only one generic open source extraction tool. Maybe there's more, and that's DMT. We have a silicon proven tool. So there's people at real foundries using models from this tool, just its HBT models. So we would need to somehow implement a MOSFET extraction flow if we want to use this tool for the Skywater or other open source PDKs. The Verilog A tools, I'm pretty sure, are unique. I don't know any other Python interface to Verilog A that comes Verilog AE that comes close to this tool. And this is a big time saver for implementation of actual parameter extraction. If we would implement EKV or BSIM extraction into DMT, we definitely need some time and funding. And we also need to come together as the experts here, like Vladek, who have actually participated in the development of the model and help us get the flow right. And we also need to do the geometry scaling equations and PDK integration. I personally think that full automation of the extraction is both unrealistic and unnecessary, at least short term. So long term, maybe. I mean, at the moment, the issue we have is not that we have a slow extraction. We have no extraction at all in the open source community. There's some guys in Australia working on fully automated extraction using artificial intelligence, and I think that's the right way to go. But this is really not our problem right now. So at Semimod, we're really good with the open source tools I have just presented. But for example, we are no EKV experts. And also, we must rent a lab if we want to measure. For example, the university people might have better access. So we must split the project between the partners if we want to have success, in my opinion. And another point is the stuff we built here, the extraction flow, can be reused for the next technologies for sure. So actually, that was my talk. These are the references. And now I hope we can have some kind of discussion to see how we can move forward.
All right, thanks, Marcus, for the update. I guess we can open up for discussion here. Any comments?
First, I really would like to thank Marcus for the presentation. It's really a huge amount of work and impressive developments. I'm a little bit biased, so I will not talk anymore. And I've seen Matthias Bucher is joining call, so he works on newest AKV3 model implementation, Verilog A coding, so he can comment also on the extraction and extraction flow as Marcus asked for.
Yes, hello everyone. From my side also, thanks a lot for this very nice presentation. Unfortunately, I didn't see the beginning of it. But Marcus Muller, you're certainly at least 1 month ahead of your time. 24th of February says down on your slides.
Oh, thanks.
That's always good. That's always good.
This is positive. He's
Yes.
really ahead of all of us. So
okay. No, I think it's very nice things you have developed, and we would be glad to cooperate with you on EKV3 model extraction and in some extent, let's say automation of that. But I definitely agree on your point of view. Full automation is maybe not really so much possible. It takes a lot of data, and maybe at that moment this is maybe not the main goal. But still, let's say to some extent this is possible, and to the extent it is possible without going into too much of artificial intelligence algorithms. I think things the kind of direct extraction for a first shot is something that could be done with EKV3 on Skywater 130. So yes, I'd be glad to interact with anyone. We have already done some work on EKV3 extraction using your tool for on the EKV3 implementation with ngSpice. I think in the last meeting, my co-worker and PhD student Nikos Makris had presented some things on EKV3. We would be very glad to cooperate with you on this, and on extraction as well.
Well, are you in a document shared by Tim and Vladek already?
Yes, actually, yes. Pardon me. We do have. We did get also actually test structures, test chips from Tim Ansel. And we've done first measurements on that, and we might actually be starting to do some modeling work very soon as well. So yes, I think things look good. As far as we can see, the process is quite nicely behaved and should not be too much of it should not pose too much difficulty for let's say EKV3 to be adapted to that. So it looks good, and okay, we will be gathering data, and we would be looking also actually at using your tool. It might take us a little while to get to speed on that, but definitely it looks extremely interesting.
So this means you are doing the extraction for Skywater, actually?
We haven't started yet. We have started doing measurements.
Okay.
So,
I mean, we are glad
yeah.
to help you with anything regarding the open source tools. So just drop us emails or something.
Matthias, I have a question for you. Is this the measurement done by Christian and student?
No, we are at TUC, Technical University of Crete.
Okay, sorry.
But we can exchange data there.
No, I think it's great to have multiple source of data measurements. So I think with CoolCAD we noticed some kinks that Boris reported. So I think if you can do some measurements and share them in this group here, that would be great.
Sure, we will be doing that. Yes.
Awesome.
We need to sort out.
Who was speaking? Because for some reason
that's Mehdi from Michigan.
Oh yes, hi. Okay,
Hi.
Nice to be talking to you, to everyone. Okay, sure. Yes, of course we would be looking forward to interacting with everyone.
Great.
So to simplify this, we have to sort out GitHub directories with measurements data. There is a directory with original MDM files for Skywater 130. I lost track of other directory where Professor Enz and his students were putting data, and now we have third source. So we have to kind of simplify directories.
I think there's some naming within the models, so you can add like EPFL or TU or whatever other university. So far, I mean, EPFL provided some measurements, but I think it's just a preliminary results, right? So whenever they have enough results, we can think about, organizing them in a better way. But the naming part should deal with, the different institutions in general.
All right, this is other point to standardize, like naming convention of the files, like technology characteristics, LW, some basic information should be already in the file name.
Yeah,
maybe Marcus has his recommendation because he is using Panda. So maybe from this point of view, one can sort out naming and directory structure, etc.
I will be glad to look at the current structure and then see how it fits to our structure. I mean, basically what we do is we have one directory for each technology. Then under each technology, we have per wafer one directory, then per die, per device, per temperature. And then inside the measurement data, we use a specific naming scheme, which is very useful. So for example, if we go here in the tool, we have defined it once, and we only use these Python objects, so that if you use them, you have always the same naming scheme. So for example, that's just the temp, and that's just the drain source, VDS, but in a specific way. I mean, some people write VDS, some people write this, and then if you automate it and you have different sources, it's a big headache. So you have to somehow make sure it's always named similar.
Yes,
so
this
if
is
somebody
what
uses
I'm talking
DMT,
about.
I recommend to use exactly this kind of structure, which is kind of documented in the software if you just look at the specifiers module. I forgot one thing. There's different websites for the tools. So DMT Core, you can find just by Googling for DMT Core, and then you will find this GitLab page. So we maintain this on GitLab, not on GitHub. But I think there's a mirror on GitHub. There's also a website for it. So if you go here to the README, you can go to the DMT website, and there the installation and stuff is explained. OpenWAF, our Verilog A compiler, has a website that also explains installation and, oh, sorry, that was the GitHub repository. Get started, you have to press. And then you see the installation here. So basically you just have to download it here on downloads and put it somewhere on your operating system. Verilog AE is described here. You can also find it by Googling, and yeah, that's it. I just wanted to put this information. I forgot to mention it earlier.
All right, maybe you can add appendix to your slide presentation and put all these links. So
Yes,
if we distribute the slides, all will have right links to all the tools you are presenting.
Yeah, that would be great. I'll put here the doc in a chat, so maybe you can just link your stuff in there, Marcus.
Yes.
Thank you.
Okay, there is a link to the Google Doc in the chat, so this should be updated as well.
So it's unfortunate that Tim Ansel wasn't here today, right? Or is he here?
I don't think so. But yeah, I think one of the points here is the funding side, right? And we've been having this discussion, right? I think Boris, you were here, right? So one of the discussion was to get Skywater to fund this effort, but sounds like.
I think we're a little bit stuck on that issue, right? I mean, Rob is driving this more or less together with me. I think there's interest, but I don't know if the dollars are there to paying for it.
Yeah, I think you are right. We are stuck on this issue. Well stated.
But you can change the problem around a bit and say, okay, other people are running characterizations tools. Can you match their tool? Can you do an open source thing? Whereas if you have an HSpice thing that runs, it's got all the models, can you just twin that?
No, this is about making physical measurements and paying for it. This is not.
Yeah, but the thing is what I'm saying is like if you get the open source tools into people's flows, then there's more incentive for them to do the other piece. So it's a kind of chicken and egg thing, but you can say, okay, from my view, what you're doing with characterization is a kind of digital twinning. You're just doing transistors to transistor models. You can also do digital twinning of block level models to, Verilog A. So you can take something which is a bunch of transistors and stuff and, like an op amp and turn it into a behavioral model. That's similar digital twinning. If you do that stuff and get people to use the open source tools at that level, then there's more incentive for them to pay for the lower level stuff as well. Because at the moment they're using the higher level, they're using HSpice as a higher level tool, so they're using HSpice characterization tools.
I guess what Boris was trying to say is measurements. That.
Yeah, I understood what he was saying. I find it's I agree. People, somebody needs to pay for that, but unless they're using the open source tools at a higher level, they have no motivation. So what you want to do is to replace the proprietary tools at a higher level to then get an incentive to get people to pay for the lower level.
Well, I think it's kind of orthogonal. Right now, the models from Skywater are kind of broken, even for the commercial use, right? So, just getting this loop here as part of this open source movement, right? Just measurements in general for each PDK, Skywater 130 or GF180, and see how things can be done differently.
Well, there's a question of like, if you actually have chips from on a Skywater process, can you just like infer the device characteristics from running the whole chip? It's kind of AI job. It's okay. Can we sort of do a federated? You do a federated learning kind of thing where you just say, okay, I'm using the same transistor models everywhere.
So
can I just sort of tune the transistor model to make the whole simulation match for my chip that I have and work out that way?
But you cannot do any analog design that way. I mean, you have to have a model in the first place to do a good analog design.
Say people have built chips. You're not getting the direct data from the fab, but you have a chip that's been built on the process. So can you just run things through the pads and stuff and see what they do and infer stuff about the process and transistor models from that? I mean, it seems like an AI job. I mean, it's something you should be able to do with any chip and any process.
Yeah, Kevin, I think that's a cool idea, right? But it's more of an emulation type of thing rather than taping out, right? You can't do that in a very advanced node and just predict what. I mean, maybe in the future, but
people make test chips particularly to do the characterization. So if you can get your hands on a test chip, it's like
sure. So I have a question for Marcus, right, and Vladik and all the people involved in measurement. So what kind of funding are we looking for here? I think it's much more of a practical question. So you're requesting some funding here, Marcus, and maybe you can add that to the Google Notes from or the document from Tim. Maybe you can share it here as well so other people can have a look at it. And
I mean, it's not that if you consider how much you pay for a license for the commercial tools per year.
Sure. But
I think it will be super cheap actually.
Yeah, but still, I mean, maybe we need to find motivation in doing that, and so far we aren't able to find that. So just putting those numbers.
Okay, I will put some numbers into the document for sure.
Thank you. All right, any other questions or comments?
I already talked to a couple of local characterization labs. We have characterization lab at TPFL with 3 autoprobers to measure wafer up to 200 millimeters. I have open call with Fraunhofer and waiting for update. There was a really interesting conversation with IHP. They are very highly motivated to contribute to open source, but the characterization lab was part of the clean room process line. It's really overloaded. So it's question of time and resources. And I talked to my old friends at the Institute of Electron Technology in Warsaw. There is a clean room and characterization lab, and they are quite open. So they can dedicate some time and share their resources for on the wafer measurements. Maybe I will try to bring a kind of summary by end of this week and share with other, and then on one of the meeting we can have also quick updates from each potential partners who has access to characterization lab with autoprobers.
Okay, thanks so much, Vladek. I think Sadayuki has some updates as well. I don't think he joined this meeting, but he reached out.
It's quite deep night in Japan.
Yeah. So maybe find a different time.
Yes, from all what I understood, there was some characterization activity within Haisin team at Hiroshima University, but because Professor Muramatau's retired, I think they closed the group. So he's searching for other partners with autoprober system.
So 1 minute, Vladek. I think I've seen, I see Christian here joining. So maybe, hi, Christian.
Yeah, hi, everyone. So sorry, I couldn't join before. I was teaching till now. So
no worries. I think it would be great to have your update maybe on measurements if you have any.
Yeah, I just wanted to just inform you that we will actually start measurements end of this week. So measurements will be done on Skywater, the technology. And we have selected a bunch of devices, NMOS, PMOS, and we're going to start measurements. So we now have received the probe, so we can automatize the measurements, and so this will be started end of this week. Hopefully we can come back. I don't know when is the next meeting, but in 1 month or.
I think the next one is on the 31st. We invited CoolCat to give an update, but after that we can have maybe.
Okay.
I think ISSCC is soon, so maybe after ISSCC or just before, up to you guys.
Yeah, so maybe we can come back with some first results. I mean, after ISSCC, we will already have done part of the measurements will be done. Then once we have the measurements, we will do some extraction. We'll do extraction for the simplified EKV first. That's the easiest one. And then we'll do also some extraction for EKV 2.6.
Great. I think, sorry, Christian, I think sharing the data would be really good.
Yes, yes. We just want to make sure that the data we share, you know, is good, you know, is good quality and can be used for further extraction.
Sounds good.
May I ask what extraction tool you're using?
We will use, so for doing SEKV, we use our Python-based extractor. And for EKV 2.6, still not clear. So either we use ICCAP eventually. So probably we'll try with ICCAP. We don't have yet automated Python-based extractor for EKV 2.6. So we're working on it, but we don't have it yet.
Marcus tool would be the best. I would strongly recommend to have a closer look.
We should try to collaborate on this if you like.
Okay, cool. So yeah, of course. So if you have better solution, that would be fantastic. Yeah. So
I mean, I don't have the extraction flow, but I have the tool where you can implement it, and then you have it open source, and then you have it in Python, without needing to pay for ICCAP.
Okay, wonderful. Yeah. We're not big fan of ICCAP. I mean, it was a useful tool, but today I think we need to move to open platforms, right? So open source platform. But Vladek, anyway, I think we're gonna meet later this week, so we can talk about that.
Yes,
and Marcus, maybe we can set up another meeting, maybe next week or whenever you have time.
For sure, just hit me up.
Okay, cool.
Okay, put me on CC.
Okay.
So one additional thing I requested from Vladek and Sadayuki to review the test style we made in MPW5, and Sadayuki started making some notes which are very extremely valuable. So maybe others can take a look as well and add their notes. And you know, it's just an improvement for the next shuttles. Maybe you can make another test tile.
Okay.
So the one you've sent to Professor Renz, it's your design?
No, the one I sent to Christian is from Skywater. That's proprietary.
The original one.
Yes. The one from MPW5 is going to come in anytime soon. I don't know when, to be honest.
Okay.
Yep.
Mehdi, do you know when is the next run?
Normally it should be on February, end of February. I should confirm that. Yep.
Because I was we briefly talked about that. You know, I have an idea of implementing some dedicated test structures for measuring noise.
Sure.
But that would take a bit more time. So
maybe we can discuss that you know, on a separate meeting with Vladek and everyone, and we can design that. We can help you or automate the generation of it.
Okay, very good.
Cool. Well, thanks for joining, Christian.
You're welcome.
And everyone.
Sounds like we're moving forward.
Yep.
Will you share the slides afterwards?
I will send them to Rob, and Rob maybe can send them.
And the meeting was recorded, so I guess there will be
the meeting is
YouTube.
Recorded.
Perfect.
The meeting is being recorded. I need to download it from Zoom and then get it up to the analog channel on YouTube. But
okay, that would be very useful for me. I missed the whole talk, so.
Yes, many of us we missed at least part of it. So hi to Christian also. Simply because it's just an opportunity to maybe connect a little bit the things we might be doing, because we have also started doing measurements at TUC on the test chips we do have. I think it would be nice if we somehow could coordinate things so that different measurements could somehow be used for. You know, you have to look at statistics as there was some things that have been mentioned on that. Of course, we having just a few test chips doesn't mean we can cover full, let's say, process variation, but still it would be useful if we could manage to have similar test, let's say, procedures and comparable files, so that we can later on gather them and do some more meaningful work, and maybe not lose too much effort for all of us doing similar work. Okay, will be good to be cooperating with everyone on that.
Okay, thanks, Matthias. Yep. All right, so is there any other comments? If not, we can just end the meeting, and thanks everyone for joining.
Thank you.
Thanks, Marcus. It was a great talk. I'm looking forward to see the slides.
Great. Thanks, everyone. Have a good day. And thanks, Marcus, again, and Mario. Bye-bye.
Sure. Bye.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye.
Thank you also for being here.
Bye-bye.
Thank you. Bye.